All right, so here we go. We're going to get started with this today. This is page 15. If your cell phones or Chromebooks are out, please put them away. So reactant molecules must collide. So what we're going to talk about is something called activation energy diagrams. Okay, and we're going to get into this page 15. Page 15 of your packet. So in order for a reaction to occur, the reactants, the molecules, must collide in a certain orientation. Okay, so this is just an example of one I tried to give you, where you can see the CH3Br plus an iodine ion, and that's a bad orientation because really, to be honest with you, hydrogen's one of the easiest elements to pull off, or ions to pull off. Okay, so I just orientated it because remember, these really aren't letters, right? These are really molecules that have protons, neutrons, and electrons. So what I was trying to demonstrate through this, and you can draw this if you want or just talk about it. Okay, this was just to give you a visual what I meant by orientation. So instead of the iodine ion trying to bond or collide with bromine or get rid of bromine or take the place of bromine, it's much better for it to orientate around. So it would move around or get into position where it can collide with a hydrogen atom, okay? Or hydrogen ion, excuse me. So that is what I mean by orientation. Again, this is just a visual to help you understand what I meant by orientation. So it might not be favorable for them to collide in a certain way, so that molecule may need to turn or adjust or be in a different orientation so that they will actually be able to successfully collide and produce products. All right, so collisions is the first one. Some of the collisions aren't super effective. Sometimes they just don't work. There's not enough force behind them. They don't collide in the right way. They don't collide straight on maybe when they need to. They collide over to the side of it. Okay, so the next one talks about rate is equal to the frequency of the collisions times how effective the collisions are. So we look at orientation, how effective the collisions are. And the reactants, this last statement right here, reactant molecules must collide with enough kinetic energy to break their strong chemical bonds. So there has to be enough force, enough energy put in to break the reactants so that you can form products. That's basic chemical reactions. Okay? We look at something, this is the piece that's really focused on for this part of the unit, is called activation energy. So note the definition, minimum energy that must be supplied by collisions for a reaction to occur. And then the piece that I think is very important here to underline or highlight, the larger the activation energy, the slower the rate of reaction. Okay? So the bigger the E sub A, because activation energy is E sub A, that's a symbol or abbreviation for it. The bigger the E sub A, the slower the rate of reaction. All right. So then the Latin 4 here on page 15 summarizes these things. It talks about the orientation, the frequency, and is there enough energy to produce products? Okay, or is there not enough energy and they just kind of bounce off each other, sort of like super balls? Okay, so those are the three factors that we will look at and that we've talked about. Okay, that gets us to understand what we call this activation energy complex. And my diagrams should be here, but they're on the next page. So activation energy diagrams are these things right here. All right, and I'd like you to be able to label these pieces. So let's talk through just a few of these. There are 5 things that I expect you to be able to label on any activation energy diagram. That's what these are, activation energy diagrams. Note that this is the course of the reaction, and this is, as you go this way, this is the course of the reaction. As you go this way, that's the energy. So your reactants are going to be the first bar you come to, because as the reaction pathway, we're going to hit the reactants, then the products. So you're going to label those bars as reactants and products. Same thing over here, reactants and products. So that's 2 of the 5 that I expect you to be able to label. Now E sub A is from the reactants to the top of the peak. So this is your E sub A. Okay. So E sub A is your reactants to the top of the peak. Okay. Same thing for this diagram. It's the same for both diagrams. So this is your E sub A. That's activation energy. Your E sub A prime just gives that mark right there. It goes from here to the top. So it's the products to the top of the peak. right, so this is E sub A prime. Same thing over here. From the, oops, I just did that wrong. Let me fix that. That's not what I meant to do. Let's talk. I need to go from to the top of the peak. I was showing you actually delta H. That's E sub A prime. Again, from the products to the top of the peak. And then delta H is, if you would draw an imaginary line over, or draw the dots over, I like to visualize it myself, then but the space between the change energy of the products and the change energy reactants, I'll talk about what that is here in a moment, is delta H. So the space between, I like to draw a dotted line over to my y-axis from both, and then I can label that as delta H. Remember what delta H stands for is enthalpy, all right? And then we really need to change this delta H down here in our notes to be an equal sign, because we're going to say E sub A minus E sub A prime. So the way we can figure out delta H is take an energy of the reactants minus the energy of the product. So E sub A minus E sub A prime. All right, so those are the 5 parts I'd like you to label. I also need you to be able to tell me by looking at a diagram or drawing it and then labeling it and then looking at it, whether it's exothermic or endothermic. Okay? So what I'd like you to think about is this is our energy, okay, on both the y-axis. I'm just drawing on this one because it's closest to me is the energy. So I'd like you to look at the change in energy of the products. So I'm talking about this space right here. Oops, it's not going to let me draw that. So the space right here, okay, between the bottom of the course of reaction to the product line. So that's the change energy. Do you see what I mean? Because this is energy, right? So if I talk about, I can use a highlighter, that would work. So I'm talking about this distance here is the change in energy of the products, right? And then if I change colors just so you can see it, this distance here is the change in energy of the reactants, right? Everybody see that? Okay. So then we would want to always label this, if I can get my board to work, the change in energy of the products versus the change in energy of the reactants. Always want to talk about the products versus reactants. All right. And what can you tell me? Are they equal? Is energy of the products greater, or is the energy of the products less? Well, the energy of the products is less than the energy of the reactants. Everybody see that difference? The yellow spacing is less than the amount of change from the beginning of the energy to the products is less than the change it took to get the purple color from the course of reaction up to reactants. Okay? And this is exothermic when that happens. All right, and then if we look at the second diagram, and I use my little highlighting tools here, we talk about this is the change in energy of the products. This is the change in energy of the reactants. So if we label it the same way, the change in energy of the products versus the change in energy of the reactants. And the change in energy of products is much greater. The yellow spacing is much greater than the purple spacing. And this is when we have an endothermic reaction. Okay. Now, for quick labeling, I've always created this and pretended like each of these were a building, and the only door to the building is at the bottom here, lower level. And I like to say if the products are about to exit, it's exothermic. Notice the products are still way up on the other floors, right? So just as a quick view, when you see your products down low and about to come out the door of the building, that's exothermic. Okay? All right, so the 5 parts I expect you to label. I expect you to know how to calculate E sub A. I'm sorry, not calculate. Delta H was E sub A minus E sub A prime. We're going to do a calculation with that in just a moment. All right, so that puts us then at the top of page 16. And I'm going to let you copy this information. You can paraphrase if you wish, and then we'll go on. Okay, so the next thing we're going to do, I'd like you to label this example 19A. I rearranged it after I saw this in class, but label this example 19A. That way we're not doing everything twice. Okay, so first thing I'd like you to do is take a moment to yourself and by yourself and label these pieces. So reactants, products, E sub A prime, and delta H. If you need to use your notes to do that, go for it. Just do that first part with me if you would, please, or for me. I'll do it up here, and you can kind of look up here and check when you're ready to check. All right, so check those 5 locations or placements when you get done and make sure that you agree. You can just do bars or you can do arrows if you want on your bars. I don't care. If you use my trick, just looking at it without thinking about change energy, you should see that it's exothermic because it's exiting out the door, so you should say it's exo. Now to justify it, we're going to talk about that E sub A products, E sub A, I say E sub A, I'm sorry. Change energy of the products versus change energy of the reactants. All right, what can you tell me? So we're looking at this space right here. This space right here versus this space right here. All right, so the change energy of products is less than the change energy of reactants. Everybody visualize that? Okay, so less than. I forgot to change pens. And what should be expected for delta H? Okay, this is our first time calculating it. Delta H, first of all, we should expect a negative delta H because it's exo. We can calculate that and show that by taking delta H equals E sub A minus E sub A prime. So if we look at our values here, and this is where you need to be careful because we're not talking about from 0, because where does E sub A start? At 150. Right, so 150 to 200, what's the difference there? 50, everybody with me? So it's 50 minus, what's E sub A prime? So E sub A prime doesn't start at 0, it starts at 50, and it goes from 50 up to 200, so that's 150. And these are generally speaking going to be in kilojoules. So we get negative 150 kilojoules. All right, so this is going to be example 19B. We're going to go ahead and label the parts on our graph. Remember to justify it. We talk about the change in the energy of the products versus the change in the reactants. So I'm going to go ahead and label mine. You can label yours and then compare. So I've labeled my 5 parts. I can look at the change in energy of the 2 pieces. Change in the products is this much. Go back to the 2-color system, change in the reactants that much. So line should go all the way down. Change in the products versus change in energy of the reactants. And you can see that this is much greater. That's why it's Indo. You also could see that your line is higher, product line is higher than your reactant line. Calculating delta H, we'd say delta H is always equal to E sub A minus E sub A prime. All right, so we're going to look and see what our E sub A is. It is from 100 to 400. So if you think about this line that you drew earlier, so that's 300. It was 100, right? Yeah. Okay, and then product line, I believe this is supposed to be right at 300, trying to be at least. So 300 to 400 is 100 kilojoules. Is most likely the unit going to be, I don't know how it labeled, so that's 200 for delta H. It is positive like we'd expect. If you think back to the thermal chemistry unit, exothermic reactions had a negative delta H, and endothermic reactions had a positive delta H. All right, so for this column, we said to do delta change energy of the products and compare it to change energy of the reactants. Here, this is going to be Indo. As I just look at these, I always think of that little trick I told you about, thinking about exiting out the door. This is closer to the exit door. If you think about the bottom of the complex or apartment, whatever you want to think of, this is Indo, and this is Exo. Okay. So the change energy of the products for an Indo, you can see it. This amount of energy is much greater than that amount of energy. Okay, this is going to be less than, again.